All right, hello and welcome. Today is Monday, April 27th. We'll start off with updates to our calendar. As you know, we're off track now. So let me give you all of those details, and then we'll do some mastering physics stuff and catch up on our work. Let's see. So. And our project was canceled. So anyway, starting with Monday. So Monday, whoa, oops, honors physics. So Monday is today. Not much, just review stuff. Tuesday we'll start looking at our test, like your study guide thing. Study guide. I'll have to make some changes to the study guide. Wednesday, of course, no stream. Wednesdays is our meeting days, right? And then Thursday, we can take questions from a review. Now that you have a chance to look at it. Friday will be our quiz bowl, which pushes our test to Monday. This is May the 4th. Oh, it's Star Wars Day. May the 4th. May the 4th be with you on that day when you take your test. So no stream next. Yeah, that is correct. All right, so that's that. So we're off by a few days, and then we'll take a look at how we can shrink our our last unit, unit 11. So unit 11 we'll shrink it as much as we can, and then we'll go into reviewing for the final, and then we'll take our final, and that'll be that. So we are almost done. We are almost done. When is the flippy due? Oh yes, I forgot about the flippy. We'll make the flippy due. So for flippy assignment, flippy, take pictures of all pages. Or you could, you can even do like a small video or video. So like in this small video, you go through all of the pages, show me everything, including, of course, the front. So include the front. Include front cover. And then you will just submit this. I mean, you should turn it in soon, but I'll give you some extra time, so we'll just make it the same day or Sunday. There you go. So we have to take pictures. Can you put the pictures in a Google Doc and do all the pages? No, just the front cover is the minimum requirement for decoration. So the minimum requirement is just the front cover for. You can put all the pictures on, like, let's say Microsoft Word, and then submit it. That works. So you can paste all images on Word. Submit one document. Yeah. Actually, I'm gonna. I don't know what type of videos Canvas accepts. That is an interesting question. Video. Let's see. Video submissions. I don't know, save it as like an MP4 or something. Usually MP4s are widely accepted. Okay. Color. Oh, I should say decorate. If you don't have color, you can make it. Grind up some powder. Use your cooking powder. Chilies and stuff. Decorate the front cover. All right. Let's see. All right, so that looks like a plan. We have our test next Monday. We'll be done with Unit 10. And that's about it. So let us see. Today, let's start with a few mastering physics problems. Some of them are starting to get harder and harder, like 11 and stuff. And number 11 says, how many 65-watt light bulbs can be connected in parallel across a potential difference of 80 volts before the total current of the circuit exceeds 2.2? So your values, of course, can be different, but this is kind of like a realistic problem in that you have a household, and in the household you have a power source. So the electrical line comes into your home somewhere. There's a main connector, and then typically your fuse box is right here, and this is what's going to check if you're drawing too much current or not. Have you done 10? I do not get it. Yeah, we did 10 last time, Chris. So check Friday's video. We did 9, 10. Yeah, we did those last time. You were here too, and you were the one who finished it off for us. So the idea is that you have a bunch of stuff that you can connect to. So these are all open. These are the wall outlets. And the more things you put in, there's 3 in parallel, and then it's series, and then it's parallel again. That was it. That was number 10. So look for things that are series, look for things that are parallel, one step at a time. Let's see. So every time I add, in number 11, every time I add an object, a light bulb, I'm going to drop the resistance of the circuit. And so when I drop the resistance of the circuit, this is my ammeter. Oops. Every time I add a resistor or any every time I put in a light bulb, so let's use the light bulb symbol, circle with the squiggly, then REQ goes down. So the goal is to find how many I can fit before the amp is exceeded. So my value is 2.2 amps. 2.2 amps. So I have to stay within this value. If I go over, then it's over. I'll blow a fuse. So using the power equation, we can figure out what the resistance of each light bulb is, right? So my power, so check your power. My power is 65 watts. Oops, not 6, but 65. The voltage is 80 volts. And so using the power equation, we can figure out what R is. Power is equal to V squared over R. And so R is V squared over P. The old switcheroo. So that would be 80 squared for me divided by 65. This gives me, I don't know, let's see, 80 squared divided by 65. It's 98.5, blah, blah, blah. So 98.4615, dot, 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 dot. I'm going to keep it. This many ohms. Okay. All right. So now, because they are all parallel, every single one has the same voltage, right? All parallel stuff have the same voltage. So now I know what the resistance is. I can figure out what my rec needs to be, and then I can figure out how many light bulbs I need, or how many resistors I can have before rec is that value, right? The other way, of course, to do it is to find how much current each one passes. So that's the alternative. I suppose it's slightly easier. So we'll do both approaches and see that they both work. So this is the resistor approach, and then we'll talk about current and then see how we can do it with current as well. So let's see. My voltage is 80. Sorry, 80 volts, and my maximum current is 2.2. So that means rec needs to be V total divided by I total. Which is 80 divided by 2.2. Which gives me 80 divided by 2.2, 36.3636. Well, that's it. That was cool. All right, so this many ohms. Okay, so by knowing this, you can say that 1 over 98.4. 615 plus 1 over 98.4615, right? And then you can see how much your rec is, with 2 light bulbs, with 3 light bulbs, etc. So with two it would be this, and this would give us well, it's just product over sum. So, and when you have parallel of the same resistor, the parallel of the same resistors like 10 and 10 would be half of it, right? Remember those patterns we were talking about? So if I had two light bulbs of 4615, if I have two, you just divide it by two. If you have three, you divide it by three. So with two, you can see how it's 49.23 dot dot dot. With three, it would be 1 over 98.4615 plus 1 over 98.4615 plus 1 over 98.4615. Keep the original number. With 3, it would be a third of it. So, oops, times 2 divided by 3. And we get down to 32.82. So this is the breaking point. So notice how, and when I put in 3, the resistance drops below the 36, and when the resistance drops below 36, then the current will go beyond 2.2. So my limit is 2. The alternative approach is the current approach, right? We know that every time we add a branch, okay, my current that is coming out of the battery has to split up. And so some of it will go through the first one, and then some of it will go through the second one, and then the rest will go through the third one, etc. Okay. Now, how much current do you get in each branch? So what is I1, what is I2, etc. Well, I1 should be, so this is the current way to solve it. Instead of looking at the total resistance, we're going to look at the current of each branch. I1 is equal to V1 divided by R1. Now V1 is the same because all of them are parallel to each other. So that would be 80 volts. And R1 is the resistor of each light bulb, which we found as 98.4615 ohms. And this gives us the current in each branch. So the current in each branch is 80 divided by 98.4615 blah 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 blah, which is approximately 0.8125 amps. So that means every time I turn on a light bulb, okay, I'm going to get 0.8125 amps. Okay. And since each light bulb is the same, every branch will send an equal amount of current. 0.8125 amps of current will go through. So now we can just do it linearly. So with one light bulb, it's 0.8125 amps. With two, it's double. Every time you turn one on, you're going to get an extra amount, the same amount of current going through the next branch and the next branch, etc. So 0.8125 times 2 is 1.625. Oh, that was nice. Okay, with 3 light bulbs, you get just a bit more, right? 2 times 3, 2.4. So at 3, you've exceeded, which is greater than 2.2 amps. Okay, my limit was 2.2. So with 3 light bulbs, we are now more than what we should be. So the current approach also works. Instead of doing a bunch of rec calculations, you can also look at the currents. Yeah. Number 12 has a bunch of switches. Let's see. Consider the circuit shown in the figure in which 3 lights, each with a resistance R, are connected in series. The circuit also contains an open switch. Alright. Oh, this looks familiar. So here is light bulb number 1, has a resistance R. Of course, the resistance R is when it's actually on. If you remember our discussion, when a light bulb is cold, it actually has a different resistance. So this branch has a switch, and it's just like the diode problems we did, where the switch can block off current, and this will change the pathway of your current flow. Right, so you get a short circuit. So without the switch on, so this is the switch off. Remember, when it's broken, it's off, and when it's broken, all of the current will go through all 3 light bulbs, and all 3 light bulbs will work. Whoa. Okay. And what is rec? Well, rec, okay, switch off. Rec is equal to R plus R plus R, because they're all in series, which is 3R. When the switch is closed, does the intensity of light 2 increase, decrease, or stay the same? Intensity is another way of saying brightness. Intensity is the same as saying brightness. Brightness. And chat, how do we figure out, well, mathematically, what do we do to figure out the brightness of a bulb? What do we look at? Is it the voltage? Is it the current? What do we look at to determine brightness? What do we in our class look at? Definitely not the lumens. We look at power. Close. Yeah. Now it is related to current. It is related to current. So current is definitely a way you could theoretically, if you can compare all the currents in each light bulb, it is possible. But then you would have to know all the resistances, etc. So ultimately, if you can determine power, that'll give you the best way to figure out how bright something will be, especially if your circuit is not all series, or if it's not all parallel and it's all like complex. So the goal is to figure out the power drawn by each bulb. That'll tell us the intensity. When the switch is closed, what happens to the intensity of light 2? So light 2 is this one here. Let me label them. This is number 1, this is number 2 here, and this is number 3. Okay, so when I close the switch, so this drawbridge closes, now the circuit looks slightly different. And our rec is also different. So here's light bulb 1. You now have a closed circuit here. So the switch is now closed. Here's light bulb 3. Okay. Now if I do the current flow diagram, of course it comes out of the battery, all of it goes through resistor light bulb number 1. Okay, now at this junction we now have a choice. Earlier we did not have a choice, right? Since the switch was off, there's no way to go through this switch, so all of the current was forced to go through light bulb number 2. Okay, by closing this switch, which means it turns on this pathway, we now allow the current to flow through here. Okay. Now, if there's a choice between, you know, a pathway that has 0 resistance versus a pathway that has any non-zero value, like light bulb number 2, which is a non-zero resistance value. That means the current will flow through the switch instead of the light bulb. Okay. Current always takes the path of least resistance, as we know. And so that means that this is shorted out. Nothing goes through light bulb 2. Nothing goes through light bulb 2. All the current go through light bulb number 1, and then through the switch, and then through light bulb number 3. Okay, so this is what we call a short circuit. It's like a shortcut. Right. If you look at the current splitter rule, the current splitter rule will tell you how much goes through. Well, right. If you have 0 on one pathway, any non-zero. So here in this switch, R is equal to 0. Of course, this light bulb is equal to R. And whenever you have a pathway that has 0 resistance, 100% of your current will go through that pathway. Now, if it's any non-zero number, then it'll break apart into 2 pieces. Now, realistically, wires have a little tiny amount of resistance. It's not technically 0 resistance, so that means a little tiny amount of current could theoretically flow through here, but not enough to turn the light bulb on. Because any conductive wire like copper or silver will be so low in resistance that the other pathway doesn't matter. Okay, so when you turn the switch on, it's a short circuit, and when you form a short circuit, all of the current flows through the short circuit. Nothing passes through the other one. So light 2 is off. Yeah. So originally it was on, it was bright. But now it's off, no brightness. Do the intensities of lights 1 and 3 increase, decrease, or stay the same? So let's take a look at the other ones, right? So now that we've closed it, what happened to the other ones? Well, our resistance actually increased, believe it or not. Yeah, a lot of people are not here. I don't know. Well, some people are lurking, so that's great. But yeah, Chapita has been missing. Okay, so what's interesting is that anytime you close off a branch... Oh wait, this wasn't parallel, it's series. I said that wrong. Anytime you close off a branch in parallel, you decrease resistance. But here, our resistance has changed in that it is because it's series. You close off something, it actually decreases. So our rec is now R plus R, which is only 2R, which means our total current has changed. I total is equal to V total divided by 2R. What was it originally? Well, originally, since rec was 3R, I total is V total over 3R. Okay, now that it's over 2R, of course you can see how it's more current per light bulb. And you can do I squared R for power. And there are, of course, many ways to solve for power. You don't technically have to have this, but power is equal to I squared R, which means in this case it is definitely a smaller value. Let's see. The current, because they're in series, they have the same current. So the current in each light bulb, so number 1 or 3, the current is V over 2R squared, and the resistance is R. So this gives us V squared over 4R squared times R, which is V squared over 4R. If I were to rewrite this, I could write it as 1/4 V squared over R. All right. What was it before? Before it was, let's see, when it was not closed, P is equal to I squared R. I was 1/3, so V over 3R squared times the resistance. This is just power of a single light bulb, so let's just call it P1. This is P1 original. P1 original is, so we get a 1/9. 1/9 V squared over R. As you can see, it used to be 1/9. It's now 1/4, so of course it's brighter now. There are other ways to explain that, and that's based on rec. Since the REQ, the equivalent resistance, went down, that means each light bulb is going to get more current, therefore it must be brighter. All right. What number was that? Was 11, right? So what is 12? Let's see, 12. Oh, 12 looks the same. Wait, what's the difference between 12 and 11? Oh no, we did 11 earlier. This was 12. Shoot. This is mastering physics 12. This is 12. We did 11. 11 was the amount of bulbs we can connect. So that was 12, and we'll do 13. Should we do 13? Yeah, let's do 13, and then 14, 15 we'll do tomorrow. So let's do one more. It's number 13. All right. So 13 is the same circuit. Oh. So consider the circuit shown in the figure in which 3 light bulbs. Oh, it says the same stuff. Does the current supplied? Oh, it's different questions. Does the current supplied by the battery increase, decrease, or remain the same when the switch is closed? Well, we kind of solved all of that in number 12, so let's just highlight. Let me use a different color here. Let's use pink. So I'll use pink to highlight all the things for question number 13. Right. So the first one says, does the current supplied by the battery increase, decrease, or remain the same? So I, what happened to I? Well, we solved it, right? I total used to be V over 3R. It is now V over 2R. Okay, so when you close the switch, did it increase or decrease? Did it get bigger or smaller? We know it changed. So if you divide by, you had 3 in the denominator earlier, you now have 2 in the denominator, therefore it is now bigger, larger. All right, and let's see, choose the best explanation from all the following. This is a short circuit. Short circuit. because as soon as you close the switch, you have a pathway that has 0 resistance, so you shorted out the second light bulb. All right. So in the process of doing 12, we kind of did 13, so that's nice. 2 birds with 1 stone. All right. Okay. We'll do the rest tomorrow. I'll open up the review as well, etc. The last thing I wanted to talk about today is LEDs and LED strips. I'm sure you've seen them. They're becoming more and more common as people are kind of decorating their places, their desks, their homes, behind TVs with LED strips, and so they shine like RGB colors and stuff. There are ones where it uses software to figure out what you are looking at on your TV or your on your monitor, and then it will figure out what is the dominant color on screen, and then the LED will flash the same type of light. So that's like a weird, a very interesting experience where you get colors and ambient lighting that matches like the scene on your screen, on your TV, or whatever movie you're watching. What does Mastering Physics do? What tells you on Mastering Physics in 3 days. April 30th, 11:59. Okay, so LED strips look something like this, where they're very flat. Okay, you'll see that there's like a if these are the RGB type. There's like a little circle thing, and then there's a little rectangle thing. The rectangle thing is a resistor, R. And the circle thing is typically divided into 3 parts to have your 3 colors. Or it could be 4, I don't know. So these are your 3 different colors. R, G, B. Right, and then you'll see that there are 4 little connectors, 4 little bridges. 1, 2, 3, 4. These are usually copper color. I should have done orange or something. Let's see. Oops. Orange. That didn't work. That took way too long. So there are 4 connectors. And then there might be like a little tiny dotted line on it. The dotted line tells you that you can actually cut it, and it'll work, assuming that the other side is connected to the power outlet. So there's like a dotted line here that tells you that you can cut it and it will work. Right? Typically the other side is connected to an outlet. So it's like and it'll be like an adapter plug or something. Usually it's like something you connect a little box to, and then you get it to your outlet. Okay, so this is your wall outlet. I don't know if you can tell. This wall outlet. Voila. Alright, so the cool thing is that you can kind of shape and resize them. So you basically have the same let me see if I can copy paste. Let's see. Copy paste. Oh yay! You have the same thing over and over. And copy paste again. All right. Boom. So this is a strip, and it allows you to cut it into size, and you can shape it whatever way you want. And of course, LEDs, remember, only pass current in one direction. The resistor controls how much current actually goes through, because each LED each LED requires a certain amount of current, that a certain range of current, really, that will work. If you try to pass too much current, then the LED might blow up or just fry itself. So the manufacturers kind of determine how much current or how much resistance you need, and you'll see that it's already embedded in the strip. And so if I have a simple circuit, here's a simple circuit. So my power source, we have a diode. This is basically an LED. It lights up. See, it's a diode symbol with a circle. The light emitting diode. And we have a resistor here as well to control how much current will flow through each LED. Okay. And this tells you that it can only travel to the right in this model that I have. If it tries to go the other way, it won't work. Typically, when you plug it into the your outlet is AC. This is AC current or alternating current, which means it's alternating voltage, and the voltage is actually sinusoidal, which means it actually alternates between going in and coming out. It goes from positive to negative. And in the outlet, the adapter thing here converts from AC to DC. And once you convert it to DC, then it acts similar to how we have a battery, an ideal battery, where the voltage is not changing. So that plug is kind of important. And you'll see that a lot of your devices have these big giant plugs. The plugs are converting alternating current into direct current. Yeah. So to convert these things, you can use a series of diodes to convert AC into DC called rectifiers or full bridge rectifiers. Consider becoming an electrical engineer to learn more about converting AC into DC. Yeah. Okay. Each little orange thing that you have is typically for each light. So if you have an RGB LED strip, you know, this could be a red light. This could be the green. I don't know which one is which, so it'll be labeled typically. This could be blue, and the other one is the negative. So every one of the top ones is the positive end, positive connector, and then the bottom one is just the negative connector. I'll just put minus here. The hot wire. All right. And then they're all connected one after the other. Yeah. Let me see if I can pull one up. LED strips. Oh, this is a 2. Let's see. So here is one of them. This thing is not RGB. It's just like, you know, white or no color or nothing. You can, you know, without reading anything, you can tell based on how many connector pins it has. Yeah, it's like 2 orange things. So that means that one of them is the positive, one's the negative, and that's all. So it's not split into different colors. Now it has 3 of them. This means it's 3 lights per patch. So you can cut right here at the orange part, and this will give you 3 lights, or 3 little LED lights. And you see this little rectangle? The rectangle is oriented vertically here. The little rectangle is the resistor. So we have a resistor for each light bulb, so each LED. So here's the yellow thing, that's the LED. And then a resistor, yellow thing, LED, resistor. This one is the LED, resistor. And then you have your 2 connectors, the orange things where you can cut. And then the pattern repeats itself over and over. And based on the connectors, you can tell how this is not RGB. This is just a regular white light. Now let me see if I can find. I don't have a camera set up. RGB LED. Let's search RGB LED. Ooh. Oh, it's not loading. Oh, this one. Uh-oh, did my stream go down? No. Oh, we're good. This one has 5. This is pretty cool. This one has 5, and 5 means there's a 4th light that is just white. So you have red, blue, green, and white, and then you're negative. Well, in this case, it says plus 24 volts. So the other ones are negative, I guess. Cool. And when you cut it, when you cut the strip, let's see. When you cut the strip at any point, let's say you just need a little bit, so you only need 3 sets. Let's say you cut it here, right? Even though it looks like the other side is not connected to anything, these 3 are still going to work, because all of this kind of cycles through all this cycles through. So when the current comes in through, let's say, the reds, it'll go back out through the other one, or vice versa. So if this was the plus 24, if this is positive, it'll go through the positive, and then it'll cycle around and then come back through the other. And if you use all lights, then it'll, you know, separate into 3 parts and go through the other colors. So even though it looks like the other side is not connected to anything, internally they're all looped around so that the bottom branch sends the current through, and it's able to send it into 3 pathways. So kind of like this. And then eventually it'll loop around and go back. All right, that's it for today. Thank you for tuning in. Continue to work on your lab, your mastering physics. I believe the lab is due Saturday. We'll talk about more things tomorrow with the lab, the review, and we'll finish off the last 2 with problem 14 and 15 in mastering physics tomorrow. Thanks for tuning in. See you next time.